So now we have, okay, let me wait a little bit more for you guys to sit down. Okay, so now it's my great pleasure to introduce Professor Rodrigo Soto from Universidad de Chile. He's going to tell us about computational modeling of active systems. Today is the first lecture. Thank you very much, Rodrigo.
Okay, thank you, Pablo. Thank you also the organizers for this school. I'm going to talk about, as the title says, some computational methods for active matter. Please ask me, I'm happy if you ask me questions at any time, at any moment, y pueden hacer preguntas en español o incluso en portugués. And, okay, I will answer in English for everyone to understand, but you can ask me in Spanish or English. Okay, so, and the slides are going to be shared by the organizers. I don't know how, but I'm going to send the slides tonight to Pablo, and then they're going to send you all the slides. Okay, so I'm going to describe how we model, or how we can model active matter in using computers, and in particular, I'm going to talk about self-propelled particles. That is going to be today. Some lattice models. I'm going to explain why do we use lattice models to describe active matter. Then hydrodynamic interactions in some relation with what Julia described is going to talk us tomorrow, probably. And tissues, if we have time. I'm not sure that we're going to get to that. Okay, so what we're going to see here. Okay, so we're going to describe some models of active matter. How do we implement them? But not only that, it's not a computational course. We're going to talk about what we can measure from simulations and what physical information we get from those measurements. And I won't talk about efficiency. Not too much. Yeah? This is not a course on high-performance computing, parallelism, and all that stuff. You can learn it from yourself, and it's not always necessary. Yeah? And most of the time, my dirty recommendation is that if you think your program is running slowly, move it to C or Fortran, and it's going to run 100 times faster. You don't have to think. You don't have to think too much. Yeah, you have to move to C or Fortran, and it's going to be faster, except for some things that I'm going to explain. Okay. So the first thing is self-propelled particles. This is a cartoon of bacteria, and we're going to talk about cartoons in these lectures. But this is a real experiment of bacteria. I think that they are E. coli, and they were tracked by hand on the 70s. And you see this nice run and tumble motion where bacteria were running in straight lines, then they change direction, almost straight line, etc., doing like this. So we're going to describe bacteria, but not only bacteria. By self-propelled particles, we're going to talk about, as I said, bacteria, but also migrating cells in tissues. Or Janus colloids, you know, these particles that are very a la mode now, that you have a colloid, that, for example, here you have platinum, here you have gold, and you put it in water peroxide, and it moves, I think, in this direction. And you have a colloid that is moving. And the key elements of self-propelled particles is that they have self-propulsion. Otherwise, it's not active, it's passive, and it's another kind of lectures. So they self-propel with a velocity that has some speed and a director. And the director changes. So that's the other element of self-propelled particles, that they self-propel and they're persistent, in the sense that the director changes but changes rarely. That it's not changing all the time. Otherwise, it's a Brownian particle. And there are two limiting cases to model how the director changes. Either you can say that the director changes by tumbles, like bacteria, that you have one swimmer like this, is moving in this direction, and then changes direction, and it moves again in that other direction. So that's run and tumble motion. And the other limiting case is what takes place, for example, in colloids, where the director changes smoothly by rotational diffusion. So the director is diffusing, following a diffusion equation. I can. So, okay, so the first case is called run and tumble particles, not very original for the name. For the other case, people choose that name, active Brownian particles. That is particles that move, and the director is changing smoothly. So the first idea that we have is to model that, saying that the director is going to diffuse on the unit sphere. In 3D is going to diffuse on the unit sphere. In 2D is going to diffuse on the unit circle. And it's the same director that Julia was talking before. And then you can say that you can describe this by the Fokker-Planck equation, the diffusion equation, for the probability of having a director, one director at a given time. So this is the probability equation. There's a diffusion coefficient, rotational diffusion coefficient, and a Laplacian in the angular coordinates. So in 2D is simple. The Laplacian in 2D is simply the derivative with respect to the angle. So that gives you the probability for the director to be in different directions. And in 3D is the same thing, but with this expression that you know, I don't know, from electromagnetism or whatever, the course you use to compute vectoral calculus. These kind of expressions. Okay, so this is one possible approach to think on what's an active Brownian particle. That is a particle where the director has a probability, and the probability evolves following a diffusion equation. But it's not what we're going to do numerically. Numerically, what we're going to do is that we're going to simulate many realizations. So we follow a trajectory, then we follow another trajectory, and we average over all possible trajectories. So that's what we say. We are going to simulate a realization of the director, and we're going to average, in principle, over all possible realizations. We're going to average over many. And there's a theorem that tells you that the Fokker-Planck equation is equivalent to a Langevin equation. And the Langevin equation, in this case, for the director, reads like that. The director is evolving on time with an intensity that is the diffusion coefficient times a noise. See, here is a noise term. It's a white noise. Cross n. So Julia used that for the cross product. I'm going to use that. Okay? So it's the same thing. And the cross product here, you know from, I don't know, mechanics, that guarantees that n is unitary all the time. And psi is a white noise. What is a white noise is, I didn't put the most important thing, is a stochastic process, that is something that is fluctuating all the time. It's Gaussian, that is the probability distribution is always a Gaussian. And because it's a Gaussian, you learn from your probability course at some moment that the Gaussian is described by the first two moments, the average and the variance. So we have to give the average and the variance for that. And for the noise, we say that the average is 0. All the components, I is x, y, and z. So all the components are 0, on average 0. That is, there's no preferred tendency to rotate in one direction or the other is rotating in any direction. And the correlation is like this, saying that the noise on two different times are completely uncorrelated. This is not real. This is a mathematical model. Actually, the correlation is something like this. Okay, at short times, the noise is correlated with the previous one, and then at long times, it's completely uncorrelated. But for active colloids, for example, for a colloidal particle like this, you can show quite easily that this is in the order of 1 picosecond. Okay, so we don't care. We don't care, and we just put a direct delta. But the physical thing is a 1 picosecond. So we put a direct delta, and we say also that the different coordinates are not uncorrelated. And the third assumption of the noise is that the noise is always fresh, in the sense that the noise at some instant is independent on in which direction the particle was moving before. Note that the opposite is not true. The director at positive times depends on the noise on previous times, because the director was obtained solving this equation. Okay, so this is what's called an stochastic differential equation. And that describes the motion of these active colloids or bacteria that do not tumble. And I think that Aparna is going to talk about the mathematics of that equation. Okay, so in 2D, it is direct to show, and this is homework for you, that equation for the vector reduces to that for the angle. Where now psi is a white noise, but now is not a vector. Here is a vector, here is just one coordinate. And the angle for the director, so you have the active colloid pointing in this direction, and this is phi. This angle is evolving like this, following an stochastic Langevin equation. Okay. So the first thing, then, if we want to model active Brownian particles, is to see how we're going to solve that equation numerically. So I want to describe you. So up to here, everything's okay? Yeah? Please ask me anything that you want. So I'm going to show you how can you solve a stochastic differential equation. I'm going to consider this simple case. That is, you have a variable, whatever, that depends on time. There's a deterministic part and a stochastic part. I'm saying that it's simple because that equation, that other equation, is complicated. Yeah. The difference here is this G here. This equation is much more complicated mathematically, is because this noise, as I said, is a direct delta, yes, like this. So if you want to plot it, it's something like this, that every time it takes a different value, but actually that goes to plus infinity and to minus infinity. It's taking values with the variance. If you take equal times, the variance is infinity. So here you're multiplying an infinite value. It's true that it's changing all the time, so it's not going to be harmful, but it's multiplying by G, and you want to say which G? The G before the kick or after the kick or during the kick? Okay, so this is much more complicated, and you can read that on Van Kampen's book or wherever book on a stochastic process. So just focus on that simple equation that is much simpler, see? No, this is white noise, but it's called a multiplicative equation. Because the noise is multiplicative with the variable itself. So the multiplicative, but it can be solved anyway. But for this equation, it's rather simple to solve it. So the first thing is that we're going to discretize time. That is, we consider discrete time steps, delta n, delta t, and we're going to say that x is the variable evaluated at discrete times. So we integrate this equation, it's a differential equation, between those two times, because this integration of a derivative is just the difference of the two x, okay? This, the fundamental theorem of calculus, and then you have the integral of that and the integral of that. So I'm going to be very naive for the method. I'm going to use Euler scheme. This is not Runge-Kutta, it's not very sophisticated, Euler scheme. So for the Euler scheme, this term, Fn, you can simply say that is f evaluated on the first value times the interval size. That's Euler. Okay. Now, what happens with this term? This is a Gaussian stochastic variable. So what is that? Okay, so we have this. So these In are stochastic variables as well, because you are summing several integral stochastic variables. So you have to sum something that is random, you get something random. Okay. The second thing is that you have to sum, actually you integrate, but it's the same thing as summing. You are summing several Gaussian variables. And there's a theorem that you learn, I don't know, in probability course somewhere, that if you sum Gaussian variables, the outcome is another Gaussian variable. Okay, so because it's a Gaussian variable, this In, we only need to compute the mean and the covariances. And that's all that we need. So for the mean, it's very easy. You take this expression, you compute the mean, and the mean enters into the integral, and because the noises have zero mean, the In have zero mean. Okay, that's easy. Then, let's compute the correlations. The correlations between In and Im with M different from N. That is this term at different time steps. Okay. Let me go back just to, there's the definition. So this is the integral ds1, the integral ds2, s1. But this goes between tn plus 1, tm plus 1. Because each I is defined as an integral over the time step. And S1, S2, you are integrating S1, for example, in this interval, and you're integrating S2 in another interval, let's say this one. That is, you're integrating over this block. Yes? But the correlation of the noise, I don't know where it is, here. The correlation of the noise tells you that it's different from 0 only if the two times are equal. That is, over that diagonal. So you're integrating here over a block where the diagonal is not there, so you get exactly 0. Cool. And now what happens if the two steps are equal? N, well, N, N. Then you have to integrate over here, for example. And now you do get a finite result. And what's the outcome? Here you have to integrate IN, average IN is the integral of these two variables times this correlation. This correlation is a direct delta. Then I can integrate over S2, gives you just 1. And then you have to integrate over S1, and that gives you the size of the time interval, delta t. So what we have get is that these IN, that were somehow mysterious, are independent because the covariance is 0 if the time intervals are different. Gaussian variables of 0 mean and variance delta t. Yes? So this equation, when we integrate down, you get that thing that was Euler's scheme. But this FIN that has variance delta t, I can write it like square root of delta t, Jn. The advantage of that change of variables is now that the variance of Jn is exactly 1. Because if you take it to the square of that, you get delta t equal delta t, so you get 1. So the integration of this Langevin equation is simply that. The delta t is included into the square root with Gn equal 1. So this is the algorithm to solve the Langevin equation or to solve the Fokker-Planck equation. Just do many realizations. Depends on your money. Yeah? The faster the computer, okay, you simulate more and more. Many realizations. You put some initial condition that can be deterministic or random, depends on the problem. Sometimes you start always with the same initial condition. Sometimes you start also with random initial conditions. And then you integrate in time. At each time step, you choose a normal variable, a Gaussian variable, with 0 mean and variance 1, and then you integrate it like that. Yes, that's it. And that's the origin of this, I don't know if it's mysterious, but sometimes you don't know why. You have here delta t, and here a square root of delta t. Yes, and this is the Euler scheme for the Langevin equation. And of course, you can do better. You can go to higher orders, but it's not so easy, but you can do it. Yes, yes, please.
On this, is it really worth
going to higher orders?
Yeah.
No.
Since it's
No, not really. Normally, you just stick to Euler's scheme. Yes, in deterministic systems, it's worth going to higher orders. In stochastic systems, it's not worth. And in deterministic systems, obviously, you need high precision if your problem is dependent on precision. For example, probably most of you have done this homework of computing, I don't know, the orbit of a satellite around the Earth. And if you do it wrongly, you get a spiral that is not good. Okay. But here, because you are adding noise all the time, if you make a mistake, it's not that serious. Because anyway, you're adding noise all the time. Yes?
I have a kind of a technical question. Can you use adaptive Euler here? For
Excuse
instance,
me?
Adaptive Euler, when you control the time steps, for instance, so that it increases or decreases depending on the behavior of the function. Yeah.
Yes, you can, sorry. The question is if we can use adaptive Euler. Adaptive Euler means that the time step is not uniform, but sometimes you get like something like this, the time steps, and you can do it directly because it's a how it's called? It's a one time step scheme. Xn on the next time depends only on the previous one. So at this moment you decide which time step, and then you move. And you have to use this square root of delta t. Depends on the delta t that you're using at that moment. Yes?
The adaptive time step or the let's go to a higher order scheme, all of that will depend on how complicated f of x turns out to be.
Yes.
The noise doesn't matter.
Yes. But beware of something. Okay, now I'm going to include, because here is very simple, but we're going to consider particles that interact, for example, like this, and they collide in some way. And normally you want to avoid large time steps because particles are going to overlap and you create big forces. So you want delta t to be small. Okay. Some time scale. You want delta t to be small, but if it's small, then square root of delta t is bigger than delta t. So sometimes you jump a lot because of noise and not because of the deterministic force. So you have to be aware of that. So to choose the delta t is not only this term that you have to take care, you have to take care also of this term. Yeah. Okay. So this is for AVPs, particles that change director smoothly. But as I said, also you have bacteria that change director abruptly. So you have tumbles like this plot here, this design. And tumbles, normally you say that there's a rate, nu, and with this rate, you choose a new director, n prime. And the new director depends normally on the previous one. Okay, but life is not that complicated to give you a full function of two variables. Normally, the new director depends on the angle with the previous one. That is, depends on this angle, alpha. So when you have tumbles, and it was measured, for example, for Escherichia coli, that the tumbles take place between minus 50 and 50 degrees, essentially. You don't have tumbles like this for Escherichia coli. It's very rare. And in some cases, bacteria tumble less, tumble more, etc. So we have to sample because it's here is 2 times stochastic. You have stochasticity because you have a rate to tumble and a probability to choose the new director. So first, how to sample the rate. And this is called a Poisson process. A Poisson process tells you that you have at every time a probability to at each time you have a fresh new probability to choose to tumble or not. Let's say like that. Or, and in this Poisson process, the simplest way to simulate it is that you have a small delta t. The probability to have the event is nu times delta t. And you have to choose delta t such that this number is small. Actually, if the delta t is not small, this is not the correct expression. Because it can, for example, if delta t is large, this number can be larger than 1, and you cannot have probabilities bigger than 1. So if delta t is small, the probability to have a tumble is nu times delta t. This is the definition of a rate. And how do you simulate that in the computer? It's very simple. You have to take a number u, uniformly distributed in the interval 0, 1. So you have a u distributed in 0, 1. you have this p that is smaller than 1, and the algorithm is very simple. You take a u between 0 and 1, and if u goes in this interval, then you accept. You do the tumble. And if it goes in this interval, in the rest of the interval, you do nothing. So at every time step, you take a new number, you compare it with the p. If it's smaller than that, you do the action. So this is the algorithm. Okay, you do the for on time, you move the particles whatever, you take a new random uniform between 0 and 1, and if u is smaller than u delta t, then you make the tumble, whatever that means for the moment. Okay, okay, this is the first step, but this is not enough because now we have to choose the new director. Okay, so how do you choose the new director? So we're going to consider first the simplest case that is not that simple anyway. The simplest case is consider that the new director is completely uniform. That is, the bacterium completely forgets its previous director and chooses a new one uniformly. So in 2D, this is really simple. You say that the new angle is a uniform variable between 0 and 2 pi. Okay, nothing to worry. That is done by the computer rapidly. In 3D, there's a temptation of an algorithm that is wrong. But I want to write it because normally you find it in codes, some student codes, and you have to do it, and you get then weird results. You don't understand why. And so the wrong algorithm is to say, okay, I'm going to take the component x uniform between -1 and 1, the director y uniform between -1 and 1, set, etc. Then you compute the norm, and then you normalize. Cool, you get a unitary vector. But here I'm plotting this in 2D because I don't know how to draw things in 3D. So what you're doing here, you're sampling an x and a y in this square box, and then you normalize. So you project everything to the circle. But you see that in these 45 degrees corners, you have more points than in 0, 90, etc. So you have an excess of directions in these 4 corners. In 3D, you get an excess of directors pointing in 8 corners, in the 8 principal axes. And this is going to give you some trouble eventually. So this is the wrong way to get a uniform director. A better way is to do the same. So you take 3 random numbers in the unit cube, between -1 and 1, you compute the norm, and then you reject and you do it again if the norm is larger than 1. That is, you reject all the corners, and you keep in the interior of the sphere. And now you scale, and you normalize. Yes? Sorry.
Can't you just pick 2 angles, like from 0 to p and 0 to 2 pi, and find a new direction, like spherical coordinates?
Okay, yes. This is another way. Okay, so this you get a uniform. There are other methods. So another method is to take phi uniform between 0 and 2 pi, theta, the azimuthal angle, uniform between 0 and pi, and then you compute the unit vector. Yeah? No. I'm sorry. No, because the equator is bigger than the north and south poles. So you have to get more angles in pi over 2. The distribution probability in pi over 2 should be larger than on the north and south poles. Yes? Okay, it can be done, and this is the method of change of variables. So you get a probability for theta that I don't remember exactly, but I think that the probability of theta is sin theta. So with the change of variable, you can sample the director. So you have that the theta is something like this. You have more probability on the equator compared to the north and south poles. And then it's okay. Just give me a minute. Yes. There's another method that is to sample Gaussian variables. It's very cool as a method. It's not very fast, but it's cool. That you take an X normal distribution, the same Y, the same set, and then you compute the norm, and then you divide. Why? Because we know from Maxwell that the multiplication of Gaussian variables they're independent variables. And is well distributed, is isotropic, the distribution of x, y. You remember, the Maxwellian distribution of velocities is Gaussian in Vx, Vy, Vz, and is isotropic. It's not very fast because you have to generate normal distributed variables. Okay.
Just to exemplify, or if we implement it in the wrong way, what is the effect in this final simulation? I will mess it up with this distribution.
For example, if I studied for a while a wetting phenomenon. I put walls and particles move and get attached to walls. They're going to take longer to get to the walls because most of the directors are pointing in these directions and not in this direction. So the process at the beginning is going to take longer because they don't move on the good direction. So you get wrong results in many cases. Yeah. Okay, so this is tumbles for the easy case. The easy case is that the distribution is uniform. Now, the not easy case, what happens if the distribution is not uniform? So, if possible, apply the change of variable method, and you're going to get the results, if it's possible. But if not, you have to use the rejection method, what is called also Monte Carlo method, or von Neumann method. Has different names depending on the community, but it's the rejection method. For example, imagine that you have a distribution in 2D for the angle, the tumble angle. For example, this is the E. coli case. E. coli case, that is more probable to have a director in the front, continuing very persistent, and is rare to tumble on pi or minus pi in 2D. So how do you get the angle? You have to get angles more probable, those angles, compared to those to those close to the opposite direction. So the algorithm is very simple. It's called the rejection method. You do a do-while loop. You choose a Q between 0 and W max, where W max is the maximum value of this probability distribution. You take an angle uniformly distributed between minus pi and pi. So you choose any value in this box. But then, if Q is bigger than this W of alpha, you reject. And you do it again. And you do it again, you do it again, you do it again, until you get a point, oh, sorry, where it is? Okay. Until you get a point below the curve. By construction, this is going to give you more probable to get angles in this region compared to that. because to get an angle here, you have many cases that you are rejected. All those cases are rejected, and only these cases are accepted. But here, almost all cases are accepted. So this is the rejection method to sample non-uniform distributions. So if you want to model bacteria and do a realistic model for bacteria, you have to use this tumble kernel and sample the director like this. And in 3D is the same thing. Now you take Q, again, random uniform. Now you get a new N director prime, random uniform unit vector. What is that? Is that. You get a new director uniformly in the sphere. You compute the dot product between the previous one and the new one. And if Q is larger than this function W, you reject and you do it again. You do it again, you do it again, until you have that Q is smaller than W. And in that case, you say that the new director is what you have elected. So those are what is called the rejection method to choose non-uniform distributions. So a homework, maybe you can do it tomorrow, is that I'm going to give you a code for AVPs, and you have to modify it to be round tumbles. Okay. Up to now is, I don't know, it's quite boring, because up to now I have been talking about single independent particles. Each one was moving, each one was changing direction, but nothing else. It's not very continuous because it's projecting via Zoom, so you don't see the movie really. Okay. So we have to include interactions. I put in the program that I was going to talk about elongated particles, but probably this is going to be the last day. So the last day I'm going to talk about bacteria like this, elongated. Today and tomorrow I'm going to talk about spherical particles, and spherical particles are not so unrealistic. First, because we have the active colloids, that they are very well spherical if they're done like this, of course. But also because active matter for me is a branch of statistical mechanics. I know that active matter for other people is a branch of biophysics, or elasticity theory, or hydrodynamics. For me, it's statistical mechanics, my background. So I use the concept of university classes. So the idea is that if you keep the same symmetries, the same global properties, the same conservations, the phenomena that you get using simple models, they're not going to be too different from the phenomena that you get if you use realistic models. That's the approach that we use in statistical mechanics, that approach of universality classes, that you can have to identify the good variables, the good conservation, the relevant symmetries, and you just proceed with a simple model of that. So I'm going to consider bacteria that are not too elongated. For example, Escherichia coli is okay. Escherichia coli is not too elongated. Bacillus subtilis is very elongated, and then you cannot consider it anyway as a spherical body. But for Escherichia coli, a sphere is rather good. Okay. So colloids are spherical, but also they are extremely hard. Normally, active colloids are made of polymers, and bacteria are made of, I don't know, lipids, whatever, proteins. But considering the speeds that they are moving, they are very strong. They cannot deform at collisions. And in practice, they are impenetrable. They meet and they do not deform because of the collisions. Remember, colloids and bacteria are moving at microns per second. tens of microns per second, very slowly, so they don't collide like hard spheres. So they do not deform, and you can consider them to be hard. And I'm going to talk about that at the moment. So how do you get the equations of motion? So I make one step backward, and I consider inertia first, as if particles, active colloids, were having inertia. So you write simply the Newton's equation of motion. Mass times acceleration of a particle. There's a friction, viscous friction, because bacteria or colloids move on liquids, so there's a friction. There's a self-propulsion force, because the bacteria have flagella, etc. And there's an interaction force, the gradient of a total potential, where the total potential I'm considering just a pairwise potentials. And now, in this equation, I take the limit of no inertia. Mass going to 0, so this term disappears, and I move it to the left, and I divide it by gamma, and you get this equation. So this is the equation of motion for self-propelled particles in the non-inertial limit, where the self-propulsion speed that we were talking, I don't know, some minutes before, is just the force divided by the frictions. And you get this gradient of the potential divided by gamma, that we call it the potential. I'm sorry, that's the standard notation, we call it the potential, but beware, because now ut has dimensions of length squares divided by time. You see it easily here. You have to get a velocity, and it's something that you have to take a gradient. So it's L squared divided by t. So the potentials here have the units of diffusion coefficients. So if you want to compare things, you have to compare with a relevant diffusion coefficient. Okay. So those are the two models that we're going to talk. We have spheres with a diameter sigma. And we said that they're going to interact when the distance between the two centers is of the order of the diameter. So the simplest model for the potential is the elastic potential. That is an elastic constant times sigma minus r, if the particles are overlapping, otherwise it's 0. And you have to take k as bigger as possible to have hard spheres, impenetrable spheres, such that the potential is not smooth like this, but rather very steep. But as before, if k is very big, then you need a delta t very small. Because the numerical scheme is going to make force times delta t. And you don't want that. You don't want that, because that means that your computer is going to run forever and is going to advance very little. So normally you want delta t's big. That means that you're going to have to use k's rather weak, and the particles are going to overlap. You have to live with that. But you have to be aware of that, because there are some theories, for example, for different phenomena, that says that something happens when the volume fraction is 0.3, for example. The volume fraction is how much space the spheres occupy. For example, for the motility-induced phase transition, it takes place at density packing fraction about 0.3. But if particles overlap, or can overlap, you can get larger packing fractions. You can compress the system more, and you're not going to get the same results. Okay, so if you are using a weak k, probably you're not going to get the same results as other people. You have to be aware of for comparisons. So normally what we do is we take a very weak K for test, for developing, for making some intuition, and then for the figure for the paper, take a larger K. Yeah? Okay, this is the elastic model, and the standard model that people use is the WCA model. That's also called truncated Lennard-Jones. Is a potential that has a very strange form, because I don't know if everybody know Lennard-Jones potential, but this is Lennard-Jones potential that has this expression, like this, where the depth is minus epsilon. This is at sigma. No. No. Sorry, this is sigma, and this is 216 sigma. So what we do is we truncate it here. We truncate it and we put it like this. And then we shift it. Okay. This is the potential that is called WCA, that is purely repulsive. So if you truncate it and you shift it, you get something like this. The advantage of this model compared to the elastic one is that the force is 0, 0, 0, 0, and then it moves to 0 again, very smoothly. So you have continuous time, derivative, and you can do things sometimes. Okay, but those are the two models that you use. Okay, so how do we solve now the problem for AVPs? At what time do I have to finish? 30, no? 12:30. Yeah, okay. Yeah, okay. So the first algorithm is a brute force algorithm that do the thing. You integrate over time, then you make run over all the particles, you assign the self-propulsion speed. Okay. Then you run over all the particles, you run over all possible neighbors, all possible partners, you compute the force between the two particles. There is a central force, so it depends on the relative position. And for the particle I, you sum this force, and the particle J, you subtract the force, because you have action-reaction, you have a potential. So that's why you do this for J smaller than I, because you don't have to compute the force between 1 and 2, and then the force between 2 and 1. It's the same force with a change of sign. So you just do it once. And then you run, once you have computed all the forces, you run over all the particles, and you say that the position is going to be the old position plus the total velocity, that is the self-propulsion speed, plus the forces, times delta t. And for the director, you do something, either AVPs, that is with the square root of delta t, or random terms, or whatever. The problem of this algorithm is that the first part runs over all particles, so it's order n. The last part also runs over all the particles, is order n, but this part runs over all the particles and all possible partners. So you have to run the system twice, so it's order n squared. So it's very slow. You don't want to do that, except for tests, except for getting some ideas. In Python, I got bored up to 20 particles. After that, okay, I turned the computer off. In C, probably 100 particles. And then also you get bored. And then you have to move to more efficient solutions. So the trick consists that you notice that both the elastic potential or the WCA potential or any potential that you use, it has a finite range. So you have a nice solution is, sorry, to do the same as before. So I'm not going to repeat the algorithm, but you run over all the particles, you run over all partners, but before computing the force, you check that the distance between the two particles is smaller than the cutoff. So you say, okay, I'm avoiding to compute the force for all possible pairs. It's a good decision. But still, you have to compare all pairs to see if they have the proper distance. So still is order n squared, the algorithm. It is better. It is better because you don't have to compute the force that normally is a complicated expression. First, you have to build a vector, to compute some powers, etc. So this takes you nothing, and your code can run, I don't know, twice as faster. Still n squared, but twice as faster. Okay, what's the good solution? There are several solutions. There are two standard solutions. In all books, and for these kind of things, maybe I'm going to add that on the, so I'm going to write it to remember later. Books. Okay, those tricks are not coming from the active matter community. They are coming from soft matter community in general, where people in the 80s developed many algorithms to simulate particles, Lennard-Jones particles, gases and liquids. And there are many very nice books where you can find the details of the method. But the two methods are the linked cell method and the Berlet lists. So for the linked cell, you take the system. Here I'm plotting a 2D system. You divide the system in cells, not any size. The cells should be slightly larger than the cutoff. The tightest, the better. So it should be larger, but not too much than the cutoff. And then you put the particles. What the advantage of that is that you know for sure that each particle at most is going to interact with the particles in the neighboring cells. It's impossible for this particle to interact with a particle here, because the distance is bigger, is for sure bigger than the cutoff. So the algorithm is like this, again, for you simulate over time. You allocate the particles in cells. You put all the particles in the cells. This is an order n algorithm. It's very easy. Then you run for over all the particles. You compute the self-reversion speed. Then for all the particles, you run on the neighborhood of particle I. So for each particle, you look for all the particles that are inside the cells of the neighboring cells, sorry. Including the cell, the own cell is running off battery. Okay. And then, yes, you run over the particles there, and then you check if those particles really interact. And if they really interact, then you compute the force and you do whatever. The cost of coding that is not that difficult. It's not that easy, but it takes, I don't know, the code can change to several tens or hundreds of lines, but if you're running your simulation for your thesis, it's worth doing that, and it's going to run much faster. Of course, you can do many tricks now to improve the code. And the other solution was invented by Berlet, that you have the particle has this interaction radius, RC, and you define a skin radius that's a bit larger, RS. And every now and then, not every time step, every now and then, you allocate the part, you build the list. For each particle, you identify all the particles, all the other particles that are in the skin, in this large region. You know that there are many of them, they are not going to interact because they are bigger, larger distance than RC. But anyway, you build the lists, and then you do again the same thing. For every particle, you run over the very list of this particle, and then if the distance is sufficient, you compute the force. Why do we use this skin? Because particles are moving. Particles are moving, so if you have a particle here that is not in the list, it can move and eventually enter into the interaction region. So you have to update the list before that happens. So, and there's a trade-off. If you do the skin very shallow, then you have to update very often. That's not good. If you do the skin very thick, you don't have to update very often, but you're considering many particles that are not worth considering because they are too far. So there's a trade-off. What's the optimal skin size? It was optimized for Lennard-Jones in thermal cases, in equilibrium, and if you look one of those books that I'm going to give you, it say, okay, it's convenient to use 1.1 times the, I don't know, interactions. For AVPs, I don't know if it has been optimized. So try. You run a code with different skin sizes, you compute the computation time, you measure the simulation time, and you choose the best. That's the solution. Okay, those are the two methods to simulate. Okay. How do I do that? I'm going to share you a code that does that, but it's a very bad simulation because it does not have the cells or the lists. Is an order n square code like this. Yeah? I do the full loop. Yeah? It's in Python. And yesterday I ran it overnight for how many particles? 67 particles. And it took me, I don't know, 10 minutes. So don't go beyond that number if you're going to try it, because otherwise it's going to run forever. Anyway, there's a status bar to see how it's progressing. Okay, so I'm going to share you the code to make some tests. What do we want to do with the code is what I'm going to describe you now. So the code is essentially what we just discussed. Not very different, except for the initial condition that I think is self-explained, and you can ask me, how do I put the particles in the system? But as I said, we run simulations. Why do we run simulations? First, just you can get a very nice picture, a video, but normally you want to do something more quantitative, and we want to measure things on the simulations. So here, today and tomorrow, I'm going to describe different things that normally you measure in non-equilibrium statistical mechanics. Pair correlation functions, spatial fields, density fields, nematic order, nematic tensor fields, the mean square displacement at the diffusion coefficient, and temporal correlation functions. And in all cases, what I'm going to show you and put some emphasis on that is how to implement on-the-fly measurements. That is, during the simulation, we're going to measure things. We're not going to record the full trajectory. Never do that. Never do that unless you want to buy hard drives every now and then, because you're going to, I don't know, a long simulation is going to generate 1 terabytes of data, then you have to post-process it. And the post-processing is going to take you as long as the simulation itself. So normally, it's better to do the on-the-fly measurements. There's a risk with on-the-fly measurements that normally you have to take some decisions. For example, I'm going to measure correlation functions up to that distance. And then, after the simulation, you discover that the funny things were happening at larger distance. Okay, you have to run the simulation again. Or you didn't measure something, and then later you discover, that field maybe was different, was relevant. Okay, you have to run simulation again. But it normally is better to compare to save all the data. Most of the things I'm going to describe you are quite easy to implement on the fly, except for mean square displacements. Normally, people do mean square displacements as a post-processing because it's easier to think for the mean square displacement as a post-processing method, but you can do it on the fly as well. Okay, so I'm going to start with correlation functions because it's very general, and this is not for active matter, it's for everything that you want to, for everything on soft matter, because probably most of you are young, and 10 years more you're going to start, you'll be doing other things, not active matter, you're going to do whatever. But most of the concepts of, many of the concepts of active matter are going to be useful there. And the tools, for example, the correlation function is something that is very relevant. So the correlation function is that you have a system, that is not working. You have a system of particles, and you want to take any of them as a center and see what's the probability of finding another one at a given distance. You can play with coins. You put several coins on your table, and you move the coins, and you're going to see that, because coins have excluded volume, that the probability to find two particles at two coins at a distance smaller than the diameter is 0, because they cannot overlap. But not only that, not only the pair distribution function is 0 before the diameter, but also if you take some snapshots, there are many pairs of coins that are exactly or a slightly larger distance of the diameter. Actually, if you take a picture, they're going to pack almost as an hexagonal packing. So there are many particles that are exactly at one diameter. So normally, the correlation function is done like this. You take one particle as a center, any. You count how many particles are in an annular region between a distance and a distance plus the air, and you count the particles, simply that. And what you get typically is that is 0 for distances smaller than the diameter. Then you get a peak, because particles are most probably at that packing distance, then goes to a small value, etc., and it oscillates. Gracias. Yeah. Okay, so how do you measure that? You do something like this. You run over time. You simulate everything that I just explained. And now, if it is the time to measure, and this is a relevant question, when do you want to start measuring? Typically after some transient, because the system takes some time to reach steady state. But also, you don't want to measure every time step, because if you have a configuration and you have a small delta t, the next configuration is going to be almost the same as the previous one. So you don't want to take the same snapshot 100 times. So you take one snapshot, then you let particles to move, you take another snapshot, etc. And now the measurement is like this. You run over all the particles. You take J in the neighborhood using brute force method, using Berlet list, using neighbor list, whatever. You choose the partner. You compute the distance between the two, but you have to be aware of periodic boundary conditions. Eventually, I'm going to describe periodic boundary conditions tomorrow. Then you compute the bin, and this is important. You have to bin the distances. So you have delta R. This is delta R. And you have a position, a distance. Yes? And you say that the bin is going to be the integer part of this division, but rounding off to the floor, as it's said here. So the bin is the int. Yes? You just take, so this is going to be bin 0, 1, 2, 3, 4, etc. And you simply accumulate. You say, on this bin, I have one pair. You run over all pairs, you get another pair at that distance, another pair at that distance, and what you start building, 0, 1, 2, 3, 4, is a histogram. Whatever. You start accumulating pairs at a given distance. I don't know what I did. Okay. Yes? And then, when you finish your simulation, at the very end of your simulation, you run over all the bins, and you take your accumulation, and you normalize to what? And this is, here's a closing parenthesis that is missing. You normalize to what? Of course, to the number of times you did the measurement. So this n measurement, G, this is in Spanish, en mediciones, sorry. It's my Spanglish coding. Okay, it's en mediciones of G. So you increment it by 1 every time you measure. So you divide by the number of measurements. You divide by the number of particles. Of course, because if the system is bigger, you're going to accumulate more pairs. You divide by the size of the bin. And this is the size of the bin. 2 pi r delta r. This is the area of this binning region. 2 pi r times delta r. And finally, you normalize by the density of the system. Why? Because if the system was denser, you expect to find more particles. If it's less dense, you're going to find less particles. So you normalize by the density. This normalization guarantees that if particles are not correlated, you're going to get 1. If particles are correlated, then you get something different from 1. Smaller, meaning that it's less probable that in a Poisson process to find a particle. Larger than 1 means that it's more probable to find particles at that distance. Okay, so this is a drawing by hand, of course, you see it. It's not real measurement, but this is more or less the picture for hard spheres or Lennard-Jones particles in equilibrium. I don't know if you have done this measurement and if you know how's the shape of G for AVPs. Any of you have done this measurement? No? It's very different. This is G of R for AVPs. Okay, for my 67 particles. Is almost a direct delta at the diameter. Yes?
Is it in the phase separated
Yeah.
regime? Okay.
Yeah, of course. Of course, there's, I'm cheating. Yeah, of course, yeah. But, okay, you know more. You know more than me. That this is as you see here in the picture, the system is not homogeneous. It's clustered, so the AVPs particles, because they are persistent, they go, they meet, and before they can escape, new particles can come, and a cluster grows. So here you have clusters, so you have many particles touching. And this is what you see here. Many particles are touching, exactly at what diameter. You have another peak here. This is the second neighbor, this one compared to this. So it's something like a square root of 3 times the diameter. And then you have another peak here, etc. Okay, so this is G of R. This is the rotational diffusion coefficient, 0.1. This is the global density, the size of the system. And you notice also that the G of R is weird because it does not go to 1 forever. It goes to 1, and then it does something like this. It reaches the size of the system, not exactly, because the size of the system is 15. Yeah. Yes. The problem here, as Leonardo says, is that here you failed in this normalization. When you divide by this, you were dividing by the area of this annular region. But if the distance is big, then the annular region does not have this size. And then you are dividing wrongly. Okay, so you never show this picture on your paper. You have to cut it here. And then you're happy.
But you should also see information about the cluster size.
Not here. Yes, okay. No, it's not easy to get the cluster size from here because the same G of R you can get if the system is made of a big cluster, made of many particles, or you have many dimers. Imagine that all particles are on dimers. So you get a very similar G of R. So the G of R is not telling you the size of the clusters. In a big cluster, you're going to get some peaks. Here you get the second peak and the kind of third peak. Yes? So it's true. So for the size of the cluster, but it's not easy, you have to see how far the peaks go. But this is for a perfect cluster. So I'm going to talk tomorrow on how you get cluster sizes. Okay, but before finishing, because we have AVPs, we can compute more things than just the percolation function. Because particles have directors now. So you have these two particles that have this director N1, N2. So we can see if the directors are correlated or not. the problem is that here is that we have three angles playing around. The two angles of the two directors, and psi, that is the angle of the relative vector that joins the two center with respect to x. Well, everything is measured with respect to x. So you have this angle phi 1, this angle phi 2, and also the angle that joins the two centers. So we have three angles, and what do you want to measure? There are many things that you think is relevant to measure. The average of the cosinus, the average of cosinus times the cosinus, whatever. But now you have to recall your course on tensorial analysis. Typically, you learn on tensors in fluid mechanics, sometimes on electromagnetism, and sometimes never. So this is the opportunity to learn on tensorial analysis. And you realize that actually psi is only fixing a reference axis. And what you want to measure things is relative to this relative reference axis. Because you don't want to average the angle, because the particles can be like this, can be like this, can be like this, so the average of any angle is going to be 0, always. But now, if you measure things with respect to psi, and this is this plot here, you have the director R, this angle now is phi 1 minus psi, phi 2 minus psi. You can compute these three things. The cosinus of phi 1 minus, I changed the letter or no? Yes, I changed the letter, sorry. Okay, it's another letter. Sin, cos phi minus psi, cos phi minus psi. That can be easily interpreted because you have the director, that vector that joins the two centers. So this is n1 times the unit vector, n2 times the relative vector. This is the average that you're computing. And you can compute the same thing with the sine function. And the sine function is the same thing, but now doing the product not with this vector, but with the orthogonal vector. This thing like this. And I'm putting cos, cos, sine, sine, and not putting cos, psi, because it's 0 by symmetry. If you do the tensorial analysis, you rapidly convince yourself that you're not going to get cross terms. And this is called the parallel component, and this is the perpendicular component. The perpendicular component is very nice because it helps you, for example, to identify vortices in your system. Because if you have a vortex like this, then G perp or C perp is going to be negative at that distance. Because you're having most probably one particles moving in this direction and the particles moving in the opposite direction, like this. Also, this quantity sometimes is useful. That is the the product between the two directors. Are the two particles are aligned or misaligned or not? It's quite easy to check that this C alpha is equal to C1, C2, C parallel, C perpendicular. It's very easy to check that. And okay, now is the code to simulate. It's very easy, but I'm not going to show you the picture because in the simulation I have the picture for that. But I'm not going to show you the picture because I want you to guess for tomorrow what's the shape of this C parallel and C perpendicular for AVPs. How particles are aligned. And this is probably the first non-trivial thing that I'm saying. Why is non-trivial? Because particles interact by excluded volume, but I didn't put any aligning interaction. Every particle is moving its director randomly, independently. Anyway, you're going to get some correlations on the directors.
How are you doing the average? How are you doing the average? Are you averaging over particles at a certain distance, or are you averaging
Yes,
overall?
okay. So then let me show you the code. So we do binning also.
Yeah.
So we do binning is when it's time to measure, you increment the number of mediciones. Yes, you run over all pairs. You compute the distance. You compute which bin you are considering. You accumulate for the number of pairs. You accumulate for the cosinus. Cosinus, okay, I'm not writing everything here. I just put cos. You understand what I mean. You accumulate for the sinus, sin. And at the end of the simulation, you compute the function g of r, as just described. And now the cosinus and sinus functions are, these two functions here, are the accumulation on the cosinus divided by the total number of particles that you measure. And here, you divide by the total number of pairs. That's it. You do binning.
Ignacio?
So the question about the correlation is also in the MIPS phase?
No.
Okay.
I'm going to present you the plot tomorrow in the MIPS case, but correlations appear always. Students, do you have questions? We have 1 minute before lunch, no? Okay, no? Otherwise, yes. There's one last question here. There, at the end, very end. So you saw that there are many typos in the slides, so I'm going to correct the typos, and I'm going to upload the slides.
My question is about, I don't mean to be much general in this, but you talk about this order parameters that we can measure in the system that we are simulating. But is it, trivial to make this, or straightforward to make the measure from the system that we want to study in experiments to the control parameters, like how do I decide to model with run and tumble or ABPs, look into a system?
Well, if you want to decide to model a system with AVPs or run and tumble, depends on your system. That is, if you are using active colors, the colors, they change direction smoothly. Bacteria, normally they do run and tumble. They run, they change direction, and they continue running. But it's quite easy for biologists to knock some genes on the bacteria such that they do not tumble, and they become smooth runners, and they are modeled as AVPs.
Oh, right. Thank you.
And also, single tissue cells, do they move more like ABPs?
They move like AVPs, except that the interaction is not excluded volume. Migrating cells in tissues, they move, they change direction also randomly, but when they meet, they repolarize in the opposite direction they were moving, and they start moving in the opposite direction. It's like a hard sphere collision, like billiard balls, if you want. It's contact of inhibition locomotion. Yes. It's not exactly that, and Ignacio Bordeaux probably knows much more on these migrating cells issues. Yes. Okay, excellent. Next. Real experience, much better. Okay. Francesco is going to.
These measures are general. If I put some self-aligning term, I would change nothing in these terms, no?
There's something. There's something, because if you put self-aligning, probably you're going to spontaneously break the symmetry, and the system is going to flock. Yes? Yeah. And if it's going to flock, then this sentence is not anymore true.
I see.
because we have now 4 angles in your system: phi 1, phi 2, psi, and the broken symmetry angle. So, and the tensor analysis is a bit more complicated, but you can get information out of that. Yes?
Okay, thank you.
Okay, so do we have more questions? Please.
Is there anything interesting that we can learn from higher order correlations? In this case?
I don't know.
I don't know.
I really don't know on higher order correlations. I have not followed the literature. It was quite a la mode some years ago on these 4-point correlation functions for dynamic heterogeneity. I have not followed the literature, so I don't know how far they reach to get something useful. Because those quantities are things that we can directly compute from theories, and probably, I don't know if you are going to talk about how to, no. But from some hydrodynamic theories, you can predict those values, and so you can compare your theory to experiment to see if it's good, doing well. And it's some things that you can easily measure, and or you can put as an input to your theory. Although I don't know how to compute the correlation, but I put this value. This value, okay, at hand. Yes. For these 4-point correlation functions, I don't know how far they reach. I have to study.
Especially in active system, I don't know if there is much literature.
No.
Reactive class people get excited about the 4-point correlation function because they know how to calculate the support coupling. There is some theoretical work out there.
In jam system, basically.
Jam,
Near
cells,
jams.
various other things.
So that's for the same reason as you mentioned, dynamic heterogeneity,
Yeah.
like
yeah.
in glass systems.
Yes.
Dynamic heterogeneity is a good metric for force distribution in tissues or something else like that. You're not necessarily looking at pair correlation functions of position. You're looking at pair correlation functions of shape, or you're looking at pair correlation functions of polarization. I mean, 4-point correlation functions.
Okay, more questions? Okay, so let's thank Rodrigo.
Thank you.